All right, everyone. Thank you so much for coming to this presentation about biochar with Ken Carloni. My name is Maggie, and I'll be introducing Ken. Ken received a master's in evolutionary ecology from the University of Connecticut, focusing on pollination ecology, and a doctorate in forest ecology from Oregon State University, where he studied the use of landscape fire by the indigenous peoples of southwestern Oregon. He spent 31 years teaching a range of biology and natural resources classes at Umpqua Community College in Rose, Oregon. If you all could go ahead and take this opportunity to mute yourselves, that would be very helpful, for I am new to Zoom and learning as we go. Upon retirement, Ken in 2018 turned his efforts to integrating biochar production into his restoration ecology projects. He is currently the education program chair of the Yew Creek Land Alliance, a nonprofit community land trust that owns and manages a 380-acre property of diverse meadow, oak pine savanna, and conifer forest habitat in southwestern Oregon. The Yew Creek Land Alliance has recently completed a 32-acre oak habitat restoration and biochar production operation on their property, funded by grants that Ken will go over in his presentation. The Yew Creek Land Alliance just begun work on with a U.S. Fish and Wildlife Service funded project to release another 5 acres of legacy oak and madrone from conifer encroachment and to convert the resulting slash to biochar. Before we begin, I'd like to acknowledge the land that we're on is Wampanoag. Ken is also a descendant of Thomas Mayhew, who established the first European settlement on Martha's Vineyard and helped impose Christianity on the local Wampanoag people at the expense of their indigenous culture. One legacy of indigenous culture across the country and the world is biochar as a product of pre-colonial seasonal burning. Ken will go over this history in the presentation, which we hope inspires people to make biochar with a full understanding of its indigenous history. And with that, I'd like to invite everyone to come to the demonstration tomorrow at 9 Sheep Pen Lane in Chilmark. We're lighting the kiln at 9 and quenching at 3. Come by anytime you want. The presentation will go for about an hour and we'll leave time at the end for Q&A. So post any questions you might have in the chat box and I will float them to Ken at the end. And again, I'm going to ask you again to mute yourselves and invite Ken Carloni to share his screen and tell us about biochar.
Okay, well, hello everybody, and I'm super excited to be here. As Maggie mentioned, I have deep roots on the island here, but this is only the second time I've ever visited. I do live in Oregon now, and that's where all of the work so far that I've been doing has been taking place. And but I've also tried to spend some time getting to know the ecosystems and the historical ecology literature from Martha's Vineyard. So I'll try and as often as I can, I'll try to bring those threads together and talk about local work and local systems that can be done here. So just a little bit about the Yew Creek Land Alliance. As Maggie mentioned, we do have 380 acres of very diverse land in Southern Oregon. And we are a nonprofit community land trust, and our mission is to conserve and restore the historic habitats and the biodiversity in our area, but also generate high quality goods and ecological services at the same time. So we're a working conservancy, and it's our goal to model how to actively manage a forest, produce products, produce services, and still not only not degrade it, but improve the quality of the landscape as we go. And we are very interested in opportunities for research, training, education and recreation. So how the heck did I get here to Martha's Vineyard from Southwestern Oregon? And here's Maggie, who introduced us here, doing a test run on one of our mills, our little portable mill here. And Maggie was working, writing for the Capital Press at the time, and which is the agricultural newspaper for Oregon, and came to Yew Creek to write a story about biochar here. And while we were there, the mill was running, so she got a chance to make some boards while we were there. And again, it's our goal to try and vertically integrate our management. So we produce biochar with the slash that's left over, and with the trees that don't make specs to go onto a truck to go to the mill, we mill them on site and make products there. So that's our goal, is for more and more of our production to not go out on trucks, but to be turned into value-added products at Yew Creek. So start with the basics. What is biochar? International Biochar Initiative, solid material obtained from thermochemical conversion of biomass in an oxygen-limited environment. We're going to be making charcoal, similar to the way it's been done for thousands of years, but obviously with a modern twist to it. So why do we call it biochar when it's just charcoal? Well, once that charcoal enters the soil, it becomes biologically active and has amazing properties in the soil, which we'll talk about in a little bit. And one of the things that really drew me to biochar is the fact that the structure of biomass, once it gets heated into charcoal and enters the soil, is stable for hundreds to thousands of years. And that carbon will never enter the atmosphere in all that time. So it's a way to sequester carbon and mitigate climate change. So why should we make biochar? Well, I mentioned one of them, of course, long-term carbon sequestration, but also in a lot of our management activities, we need to reduce those hazardous fuels so we can minimize wildfire risk. And you've probably been reading in the newspaper, we've been being hammered in the West with wildfires. The char retains water and nutrients in the soil, therefore increases productivity and decreases the production of smoke and greenhouse gas compared to the typical way that slash is treated, which is just pile it up and burn it, and it all instantly goes into the atmosphere. So getting into the sort of theory and practice here, I've set this talk up in really 5 parts. Talk a little bit about the history, science, the technology of actually the nuts and bolts of getting the work done, funding sources for projects that you may want to do, and then research needs, because we're in our infancy. The biochar industry, really the term biochar was coined in 2007. So a lot of what we're doing is brand new stuff. We're kind of, writing the book as we go. Terra preta soils, the first inkling that we had that biochar, could be active and important in soils is when soil scientists discovered these very rich, very productive soils in Amazonia. And they were, as it turns out, they thought they were whole, completely different soils, but what they just realized that they were the local soils amended with charcoal. The ancient peoples of Amazonia had been doing this for at least 2,500 years as a way to maintain productive soils in an area where soils are notoriously nutrient poor. In the Great Plains of the US, in the neighborhood of 50% of the soil of the soil carbon is charcoal. And the Indians would burn off the landscape on a regular basis. The heat would go into the ground and char the biomass that wasn't combusted, would pyrolyze into biochar. In our area, this is right close to where the Yew Creek property is. A pencil sketch from 1841 shows a pall of smoke coming up in the background. The Indians burned the landscape regularly. There's lots of pioneer accounts of this happening. And one of the kind of beauties of doing historical ecology in the Northwest versus the Northeast is that contact with native folks only happened, about 200 years ago in the West, where it's 400 years ago here. So our history is closer to the present, and we have more sources of eyewitness accounts and more ecological data to help us reconstruct these historic landscapes and the processes that maintain them. And even in the uplands, grasslands were being burned, everybody accepts that, but fire was carried into the uplands as well to open up forests and provide travel corridors along the surface that you can see here along the ridges where they traveled, and also to burn out hunting camps in the areas along streams where Indians would move up in the summertime to hunt game and collect huckleberries and those kinds of things. They moved down in the winter to get out of the worst of the snow. Fire history in Massachusetts, there's an eyewitness account by Thomas Morton in 1632 from Quincy, Mass, right across the way here, that the savages, and recall that the word savage comes from the French word for wild. So it doesn't have the connotation then that it has today. But they set fire to the country in all places where they came because it would otherwise be so overgrown with underweeds that it would be impossible to pass through and to garden. And so in the West, where you can clear a forest with fire because conifers are flammable and you can burn down a forest and make it into grassland. That was not the case in New England, and particularly on Martha's Vineyard, charcoal values from lake sediment cores have shown that fire was common probably as a result of the high Indian population, but it didn't result in clearing of the land because hardwoods, oaks and beeches and hickories won't crown, the crowns won't burn. And so the Indians underburned here to create an open understory. But it wasn't until Europeans arrived with crosscut saws and plows that large extensive open areas formed here on Martha's Vineyard and in the Northeast in general. And I became curious as I started doing research on Martha's Vineyard, and I became curious what Martha's Vineyard. Well, Bartholomew Gosnold that discovered the island and in Nantucket and the Elizabeths, named the Martha part is after his mother-in-law and his daughter, but there's nothing anywhere in the literature that I can find about vineyard. Why vineyard? Clearly there were no vineyards here. But fox grapes and summer grapes that grow on the island have highly flammable leaves that you can burn off. They're fire tolerant, they resprout after fires. And so forest underburning would have helped keep them out of the canopy, making harvests more efficient and safer, and would have created these scrambling vines of very delicious, very important food for Wampanoag people. Soil carbon loss is global. Soil degradation, happens, to some extent more severely in some places than others, all over the world. Biochar production can help reverse that trend. And so, looking at this graphic here, where if we start in the small and fast category, and we look at molecules that are very fast and interact very rapidly, and add molecules together to create organisms, organisms into populations, populations into community, and so on up the hierarchy of life, we see that adding elements of the systems below create new emergent properties on each step of the way up. And biochar has effects at all of these levels. And that's how I'll kind of organize my next discussion, my brief discussion on biochar science. So a quick discussion of chemical bonding patterns that are promoted by biochar, how it affects pH and ion exchange in the soil, and the molecular structure of biochar and the microstructure of the plant material that gets charred. Soil microbial ecology, the fact that char in the soil greatly increases the diversity and the beneficial effects of microbes in the soil, building that up to forest ecology, how these all ramify up to affect the forest as a whole, and then ultimately to the global carbon cycle. All, biochar works from top to bottom in that hierarchy. So producing biochar is not combustion. Combustion happens when you get white ash in the bottom of your wood stove, right? This is pyrolysis, which bakes the wood in the absence of oxygen into charcoal. And you can see that the cell structure of the original wood, it remains in the char, and it creates an extremely large surface area of the char. And then you can see how the lignin and cellulose, all these ring structures, get condensed into these layers of graphene, which actually can act as a conductor. Graphene is used in the semiconductor industry to do all kinds of interesting things. And it has all kinds of interesting effects in the soil. It acts as a little tiny grid in the soil for some organisms that are getting rid of electrons and some organisms that are picking it up. And we could have a whole hour-long discussion of all the cool things that happen to biochar in the soil. But, and if I do go over these, some of these slides a little quickly, remember that this is being recorded and you can look at this later. And also at the end, I'll have my email address, and you can certainly send me your email address. And I have a case history that's written up on our work at Yew Creek, and I'll also make that available to you all. So biochar molecular and cellular structure, it increases soil pH. And in most parts of the world, that's a good thing, because most soils run a little on the acid side, especially here on Martha's Vineyard. High ion exchange capacity, so it sticks soil nutrients to it so that they don't leach out of the soil and they remain available for plant growth. It absorbs and retains water, promotes soil aggregates and therefore aeration. It's a substrate for beneficial microbes, and as we've mentioned before, it sequesters that carbon for half-life in the soil is calculated to be about 1,000 years. This is a very complicated slide that I won't explain, except to say that pH can shift the balance back and forth into what nutrients adsorb onto the biochar and what nutrients are made available to the plants that are growing in those soils. And so, as you can see, nutrients, the major nutrients that plants need to grow are sensitive to pH. And so this sort of slightly acidic category here is going to give you the most availability of most of the important nutrients. And so soil, as we mentioned, biochar pH is relatively high. It's relatively alkaline. And so it can help bring some very acidic soils up to the slightly acidic category that is ideal for plant growth. Holding water, here's an experiment that was done outside of Spokane, Washington, in wheat, where you see the dramatic increase in growth of wheat with biochar amended soils, 8 tons per acre. Iowa corn, 15% better water retention during a drought year in 2012. Biochar can seed the formation of soil aggregates. And so soil tilth, as it's sometimes referred to, is not only about the minerals and the nutrients in the soil, but also about its ability to be able to absorb water and to diffuse gases. And so aerobic soils that are very light and fluffy and allow oxygen to diffuse in discourage plant pathogens, they discourage methane producing microbes, and they discourage denitrifying bacteria that release a lot of nitrogen to the atmosphere, and encourage plant growth promoting bacteria and fungi. And so here you can see a couple of slides here where these growth promoting bacteria adhere, and the hyphae, the filaments of mycorrhizae that's a very important mutualism between plants. The fungus increases the absorptive surface of the plant roots to absorb more water and more minerals, and in return, the mycorrhizae gets to steal some sugar from the plant that it's making through photosynthesis. And so it's a very strong, very important mutualism found all over the world, and biochar definitely promotes that. As we mentioned before, it's very stable. So if you look at the fate of uncharred organic matter. In a few years, that microbial activity breaks that down and releases that carbon dioxide to the atmosphere. And so biomass is a short term or short to medium term. I mean, if it's a big log, it will hold on to that carbon for decades, maybe centuries in the Pacific Northwest where we have really big trees. But biochar will hold on to that carbon for centuries and beyond. So just a review here, biochar and soil productivity increases water holding capacity, aggregate stability, aeration, decreases soil density, which means soil is lighter because there's more air spaces in it. It sequesters toxins, so it can be used, say, in areas where there are mine tailings leaching into the water, into the soil, to capture those toxic materials and hang on to them, and increases the diversity of the soil microbiome, increases the nutrient uptake of plants, decreases toxin uptake of any toxins that might be in the soil, decreases oxidative stress, increases photosynthesis and water efficiency. So all of this simple little chunk of char can have some really profound effects. So scaling up to the forest, biochar plays an integral role there too. If you look at the, almost 500 million years ago when the first plants came out on the land, look at fire, follows them within some tens of millions of years. So plants and fire, and therefore biochar, have co-evolved ever since there's been plants. Okay, fire has been an integral part of forests and plant systems for all those years. And where there's fire, there's char. Where there's char, there's soil interactions that have had hundreds of millions of years to evolve. So out west, and to a certain extent here, and potentially in the future here on Martha's Vineyard, and we'll talk about the change in forest structure here over the last few hundred years and how your forests have become more flammable. In the West, we want to keep fire on the ground. That doesn't kill the trees because it doesn't crown in the conifers, and it also adds nutrients to the soil, more biochar in the soil, and many species of understory plants and the trees around them are fire tolerant, and they have coexisted with fire. The interesting thing here is that ground fires produce lower temperature biochar, crown fires produce higher temperature biochars, and obviously, as you can see here, a lot more mortality. And that diversity of temperatures at which biochar is formed produces a range of biochar activity. So higher temperature biochars have particular characteristics that lower temperature biochars don't. And so the combination gives you a wide range of soil properties that are beneficial to plant growth. And then this little graphic shows you that there's a sweet spot kind of right in the middle between 450 and 550 degrees Celsius. That's the target that we shoot for. That's what our kilns are designed to do, is to give you is to heat the char at about that temperature. And obviously you can see there are differences in the characteristics over here versus over here. So biochars of multiple temperatures would give you those multiple characteristics. This is a satellite image of the old growth forest just to the north of our border is right here. Actually, I took that photo looking down toward the bottom of this old growth forest and into our meadows and savannas. This is a timber company that's our neighbor that has created, the most flammable forest, probably in the world, right here. And so if you look at all the crowns here, there's nothing to keep fire from running from one crown to the other, as we saw in that photo with the fire NATO going on. That was a plantation versus that underburn, which was an old growth forest, because it's harder for the fire to jump from crown to crown to crown. So these are the most fire resistant, same species. Well, largely, these are all pretty much monocultures of Douglas fir, but many of the same species here, but yet night and day flammability between those two. Here you can see where one of those plantations burned. And actually, this is the fire that had that fire spout that I showed you a few slides back. And if you look at the only green left on the landscape, that's the old growth forests. These plantations are highly flammable, and sooner or later, the timber industry is going to come to a reckoning about how they do forestry here in the Pacific Northwest, and move to a more selective style of forestry or group selection rather than clear-cut plantation forestry. You see everywhere there's a clear cut, the satellites picked up high heat, everywhere you see it. So, and then if you look at the old growth forests that haven't been cut, very low intensity fires, a lot of survival of trees left over, a lot of diversity in the understory because of that. And then just your basic carbon, global carbon sources and sinks. Carbon's always in flux. It's being pulled into the biosphere by photosynthesis. It's being released from the biosphere by respiration, just as I'm doing every time I talk. I exhale and some carbon dioxide comes out, and also combustion. And so between combustion and respiration, there's our sources into the atmosphere, photosynthesis, and to a certain extent, other processes in the ocean are the sinks that pull it back in. Right now, unfortunately, our sources are greater than our sinks. Carbon dioxide is rising in the atmosphere, and it's having very demonstrable effects on climate, and particularly where we are right now, but many other parts of the world as well. So everybody talks about the weather, nobody ever does anything about it. Let's do something about it. Okay, so making biochar, as I said before, is going to capture that carbon, sequester it, and improve forest growth, which is going to capture more carbon through photosynthesis. So this is a report that's due out, within weeks. We've been working on this for, a year and a half, and 40 biochar scientists and practitioners with experience in large centralized plants, with mid-sized mobile plants, integrated on-site biochar production, which is what I and my colleagues are involved with. And then large-scale agriculture. The fourth group is writing about large-scale agriculture, and then the folks in municipal waste treatment who are trying to get cellulose out of their waste stream so that what goes into the landfill is just truly belongs in the landfill, and it doesn't have other places that it can go to form a useful product. So they're trying to move compost out of their waste stream, compostable material, and cellulose out of their waste stream. And as we'll see, there's a potential marriage between those two things that's beneficial for both. But particularly on the island here, where all of your material gets transferred back to the mainland, anything that you can move out of that waste stream is going to save you money and produce potentially important products as we go. So these large fixed plants, we're talking tens of millions of dollars. Most of them are cogeneration plants. That is, you burn the biomass and it and heat water in a boiler, make steam, run it through a turbine, and make electricity. And then the biochar is a byproduct of that. When they clean the ash out of their boilers, they can sieve the biochar out, and that's the stuff that's available at $150, dollars per yard that you can get, brought in on a truck and spread, 8 tons per acre on your soybean fields. Okay, so mostly cogen plants, and the efficiency of biochar production ranges with the value of electricity, because you want to burn it as completely as you can to get the most power for your electricity. But if you're not getting as much of your electricity and biochar is up, well, you tune your system so you make more char in that ash. And so that's how these very large plants work. They're mid-sized plants that can be moved and set up in areas where there's a lot of biomass. For example, in an area that has been recently logged, where all the logs have been taken off site, but all the slash and the branches, the tops and so on, can be yarded up to the landing. That's where plants like this work really well. So you take them out to where the feedstock is, so that you don't have to transport the feedstock into a centrally located plant. And there are also machines that are tracked, these air curtain burners, that have to be loaded by machinery. We're looking at probably $1.5 million worth of equipment there. And so it's not a trivial thing to work in that area. Very high capitalization costs to get those businesses going. Biochar must be charged before use. If you were to just take raw biochar that you made in a backyard kiln and put it into your garden, you might wind up with a pretty poor yield that next year because it's so hungry for water and hungry for nutrients that it's going to pull a lot out of your soil and adsorb it to the biochar that's there. So you want to make sure that before you add it to your soil, you compost it, you add urine and manure, commercial fertilizer if you're into that, NPK. And in our case, since we're producing biochar as a service and not as a product, as an ecosystem service, just spreading it out on the forest soil allows it to gradually charge as it works itself into the soil. And so you can see composting here with biochar can happen at a very small scale or a very large scale or anything in between. And here's where diverting wood from your waste stream and compostables from your waste stream can join into a superior product for improving agriculture. So our little niche in the world is integrated on-site biochar production. That is, we are integrating the production of biochar in with our forest management. This could also be done in a nursery situation where you have a lot of prunings and vineyards, any place where you're producing a lot of cellulosic waste. You can integrate biochar into that process. Instead of just piling it up and burning it, you can produce a material that you can then add back to your operation to improve soil health and improve productivity of the whole system. So what we use are called flame cap kilns. So I'll talk to you about the design of those. And then the operation, safety, feedstock handling, loading, firing, feeding, quenching, okay? So here's the basics on flame cap kiln physics. In a flame cap kiln, you load it exactly the opposite that you would load a wood stove or a campfire or your fireplace, right? Where you're used to putting little stuff on the bottom and big stuff on the top because you're interested in combustion because you want to stay warm, right? Here, when we want to make biochar, what you do is you put the fine fuel on the top and the heavier fuels on the bottom. You create a flame cap so you have flame evenly burning across the top of the kiln. When air is heated, it rises. And so you see the air, the convected air will come in from the side and feed the flame cap with oxygen. But that flame is continually pushing oxygenated air up and away so that that oxygen doesn't leak down into the bottom of the kiln where you would get combustion. Instead, it's discouraged from going down into the bottom of the kiln, and therefore you get pyrolysis and you're baking your wood into biochar there. So that's all flame cap kilns work this way. So considering kiln designs, I mean, this is the Wild West. The contracts that we've gotten from the Natural Resources Conservation Service and the U.S. Fish and Wildlife Service, which I'll talk about coming up, are all kind of very, very vague because we're on the ground floor here. We had the first we started in 2018. It was the very first NRCS funded contract in Oregon. And we're just an acre into a 5-acre project that a demonstration project they're doing with National Resource, with the U.S. Fish and Wildlife Service. So the kinds of things that we think about are, of course, efficiency, the materials, how difficult these things are to fabricate, how portable are they, and then modularity and scalability. Can you take the same modules and make them bigger or smaller or change their configuration? So looking at all those kinds of technologies that I talked about, and then looking at the efficiency, our little flame cap kilns are right up with the best of the high-tech processes in terms of capturing carbon in biochar. And so looking at this, you would say, okay, what are the alternate fates? What would happen if we did what most people do with logging slash, and that is put it in a big pile and burn it? You're going to get 99% as CO2 and other gases, and maybe 1% or 2 as char. With our flame cap kilns, it's about 50-50. You know, our numbers aren't quite there yet, but we haven't yet gotten the grant money to do good measurements and good replicatable studies to really know. And that's the case with a lot of our end of the spectrum, is that there is a deficit of research to establish the numbers that we're actually working with here. And I'll talk about that a little bit more later. Why is that important? Why is it important to establish those numbers? But the point here is that we're diverting, you know, 50% of what would have gone into the atmosphere into very long-term storage in the soil. So various designs, they're all over the place. Everybody who's got a cool idea and a little bit of skill is building a flame cap kiln. Some of them are very simple, made from 55-gallon drums. And the one that we're going to be using tomorrow is similar to a kiln that I designed for folks that I've been working with on the island of Guam, where 55-gallon drums are all over the place, and people don't necessarily have a lot of money to build fancier kilns or fixed plants. And so this is very similar to the one we're going to be using. This is the one I designed for Guam to connect these barrels. And this is the particular system I used. Maggie and I used a different system for the kiln that we'll be putting in tomorrow. You know, this is all, you know, everything we do is experimental. Everything we do, we're figuring things out as we go and learning as we go. Kontiki kilns, because they're cone shaped, I think. It's just sort of a pun on those. Some very small, not much bigger than a wok. Some quite large, varying efficiencies, varying expense, varying difficulties to make. This is the workhorse of the Oregon system right now, the Oregon kiln. We use these and 5 other different kinds of kilns. You know, these were sort of the industry standard at the time we started, but we kept tweaking our kilns and making them better, making them more efficient, making them easier to transport. These are 200-pound kilns, and bucking them through the woods, you know, through this kind of stuff can be challenging. And so what we've been trying to do is make our kilns more modular, lighter, easier to move around, easier to configure based on the feedstock. And so I'll show you some of those. Oh, this is a big box kiln. One of our colleagues in Utah, Darren McAvoy at Utah State University, has been doing these very large scale kilns, machine fed, wide open spaces kind of thing. Kelpie Wilson has designed the Ring of Fire kiln. She is the guru of biochar in Southwestern Oregon. She's done terrific work all over the US and various parts of the world. She's one of my heroes and a good colleague and a good friend. Her kiln is designed as a double-walled kiln. We both kind of brainstormed this double-walled idea out. Her kiln looks like this. I'll show you mine in a minute. Very similar technology. So instead of just a flame, air coming in from the side, the air comes up through a slot at the bottom and feeds the flame cap from the edges. This carries a lot of heat back into the kiln and makes that kiln more efficient. More heat stays in the box, higher efficiency charring. And then the kiln that I've designed is this framing is just rolling barn door stock, where the little trolleys roll through the door and you roll your barn doors out of the way. But the beauty of it is that it slots together and locks together, and I can configure, this is a 4x4 box, square box. I've configured them into 4x12 rectangles, which are great for Douglas fir boughs and conifer boughs. You chop them off and throw them in. So a lot less slicing and dicing with these larger kilns, and especially those long, narrow kilns. Whereas more brushy material, branchy stuff, hardwood stuff, the configuration into this 8-sided kiln here, they all stack nicely here. The slots, here's the slot at the top where the air feeds the flame cap. Here's the slot at the bottom where the air comes in. Notice this is a fully engaged kiln. That's been burning for an hour. And notice how little smoke is coming out of there, because as the feedstock is heated from down below, the gases that come up through, including the smoke, the particulates, get burned by the flame on the top. And mostly what you get is just clear gas coming out over the top. And this, by the way, is green feedstock as opposed to dry. And I'll talk about that in a little bit. But, you know, you would think green wood in there would make a very smoky fire. But once you get that flame cap going at 700 or 800 degrees Celsius, it burns everything. So how do we operate these things? Safety, feedstock, loading, firing, feeding, and quenching. Let's go through that. So personal safety gear, no synthetic clothing. You get an ember landing on your nice synthetic gloves and you're gonna have a good old blister there, right? So cotton, wool, you know, non-synthetic stuff that won't melt on your skin. And then the various tools, of course, to scrape the ground to get it set up for the kiln, and fire swatters, which are awesome for putting out little flames as they're starting to creep along the ground. Welding gloves, not absolutely necessary, but when you're tinkering with the kiln while it's burning, kind of nice to have. So here's what we had. Here's what we started with at Yew Creek. We had forests like this, you know, typically surrounding these centuries-old oaks and madrones out there that were dying because these conifers were choking them out. And so the NRCS was paying us to liberate these, you know, release these legacy oaks and to char the slash that we created when we did it into biochar. So here's what we started with. Here's the kind of forest that we have now. An aerial view. This was before thinning, and this was after thinning. It's exactly the same photo. And so we created a fire break here between us and another really flammable plantation below us to the south. If fire comes through here, we have a chance of laying it down here on the road, either stopping it on the road or at least getting it on the ground so it underburns our forest, where we've now separated the crowns to make a much more fire resistant forest. Taking a look here at Martha's Vineyard, looking at your land use allocations, your Corellis forest in the center of the island is about 8% of the ground. Land conservancies, little bits and pieces all over the place here, that's about a little over 13% of the ground. So 21, 22% of your land base, even including the Elizabeth, that's including Dukes County, including the Elizabeths, is where the majority of your biomass is and the majority of your fire risk. And so part of your fire risk is not only because of the suppression of fire for hundreds of years, but more importantly, because of the conversion of your forests from hardwood forests to pine-dominated forests. And it turns out that white pines and red pines, which are the majority of the conifers that were planted in the Corellis forests, are not, you know, they're native to New England, but they're not native to Martha's Vineyard. And so in an effort to, first of all, try and save the heath hen, which didn't work because that went extinct, after the forest was established, they thought, oh, well, we'll plant pines here because pines make lumber. And that's the right thing to do with state land. And, you know, and it was obviously well-intentioned, but unfortunately, this is not a good place to make timber, for lumber. And you've created an incredibly flammable forest there. And the fact that those pines, those two species of pines were imported, those seeds fly all over the island. And now you've got stands of pines that never existed here when these were highly fire resistant hardwood forests. They're now very, very fire sensitive conifer forests. So back to Oregon, marked our trees. Notice we leave the biggest trees and take the smallest ones in the stand. And then buck them up, get it into small enough pieces that we can drag to our kilns. Machine piling, bad idea. The hardest work I've ever done in the woods was taking apart machine created piles to put into kilns. It beats up the soil, gets a lot of dirt in your piles. And of course, piling and burning, just you waste all of that potential to capture that carbon, dump it all into the atmosphere immediately. So stay away from that. Staging your material ahead of time. You'll see how, Maggie did a beautiful job staging the fuel that we're going to be using tomorrow, all the butt ends facing in one direction. So you just grab it and pull it instead of everything being locked together and it being flat dangerous to get up on those piles and start beating them up to get the fuel out of there. Green feedstock. I mentioned you can use fuel green. We did an experiment where I loaded up my truck and we weighed them on scales. We measured the moisture in them, subtracted the moisture, and then sent the char to a lab and found that in 2 different runs, we got 30% on one run, 41% on the other run. So there's a lot of variability, but still we're working our way to that 50% carbon capture. And you can do it with green feedstock and you save labor because the fewer times you touch a piece of wood, the less it costs you to treat that wood. So 4-inch diameter seems to be the sweet spot. Bigger stuff leaves a lot of charred logs left over, which are not necessarily a bad thing if they're just going back out onto the forest floor. But if you want a more uniform material, you want to get 4 inches or below. Anything bigger is an ecosystem resource, habitat for salamanders, slow decay, and so you're not going to release that carbon to the atmosphere for quite a while. Loading and firing, again, big wood on the bottom, and big wood right on the bottom actually protects the soil better than smaller. Then your finer fuels on the top. I'm torching this off with a propane burner, and there's a fully engaged flame cap there. Okay. Now, if you're charring green, this is one of my colleagues who's lighting it from the bottom edge of the kiln. It burns into the kiln and suddenly now there's not enough oxygen, there's a lot of water, and you get this big pall of smoke. There's one of my former students who's now working for the NRCS, lighting the kiln from the top, and you can see as it burns down in with plenty of oxygen, it's eating that smoke as that smoke rises. Even that smoke there will burn up in these flicks of flame coming up here. You get a full kiln and you're ready to go. With these modular kilns, you can unhinge the panels, pull them apart, rake them out, and spray them with water. That stops the pyrolysis. If you just left it there, this would turn into a pile of white ash by the morning. The water decreases the temperature, stops the combustion, so all you get left is the pyrolyzed char in the bottom. How can you do this? How can you do this yourself? How can you qualify to get a grant to do this? The NRCS has what's called their Conservation Stewardship Program. And if you qualify for that, and folks who are in agriculture here, folks who have tracts of land with lots of forest on them, your 1 or 2 acre parcels are probably not going to qualify, but if you got together with some of your neighbors, you might qualify for this. To produce biochar from woody residue using the woody debris remaining after fuel reduction harvests or wildfires to create biochar. So there's money available to do this from the feds, because the feds have recognized that biochar is an important material that can mitigate climate change and improve soil health. So they're supporting it with dollars. However, get it in writing. Most NRCF staff are new to the biochar, don't always know how to advise or specify. If they don't, they'll get technical assistance from, Oregon Department of Forestry or CAL FIRE in our area, various other, probably they go to the fire chief in this area. But there is an urgent need for more trained contractors and consultants, maybe some of you out there, because a lot of this is education. You need to educate the folks who are helping you who are going to give you the money to do this. So you make sure that you write the prescriptions correctly and that everybody understands, what's going on, and there are no surprises later on down the line. As I say, we've just started a pilot program with U.S. Fish and Wildlife Service, and hopefully they will make this a regular part of their Partners for Fish and Wildlife program. Maggie and I were talking yesterday about some of the ponds, some of the smaller ponds here that are getting agricultural runoff and causing a more eutrophic, a higher nutrient load, algae-ridden ponds. Biochar in swales where that water is running into those ponds can capture some of those nutrients, keep them in the terrestrial side of things, and actually make that water clear. And that's something that U.S. Fish and Wildlife would absolutely be interested in. So another thing about it is that piling and burning, costs a certain amount of money. We do everything that a hand pile and burn contract does, and then we have to put it in kilns and light it. So there's always going to be an extra cost to doing what we do versus the standard just pile it up and burn it. So what we need to do is, you notice that these axes don't have any numbers on them because these are all theoretical graphs. We don't have the data to say how much, carbon, what is the payback period? Remember I said earlier that producing biochar is initially carbon positive. We put a bunch of CO2 in the atmosphere while we're making the char. But since we store that char for such a long period of time, that pays back after a certain time. We don't have the research yet to put numbers on these charts. We need to do that so that that public and private funders who are going to be paying for this know what they're getting. And the other thing is that gives us access to carbon markets, because if we can quantify how much carbon we're saving, we can trade those on offset markets, and that would make up the difference between a pile and burn contract and a biochar contract if we get the credit for the carbon that we sequester. Okay, but the problem is with that, right now, the NRCS is paying by the acre. Well, every acre is different. And so we need a better tool to be able to say how much feedstock is on the ground and how much are we going to convert. And the NRCS and whatever government agencies need to pay by the ton instead of pay by the acre. And so there are emerging technologies, especially LiDAR technology, which can see the canopy top and it can see the understory, so that we'll be able to say, okay, this acre has X amount of tons per acre, this acre has less, this acre has more. And that's how agencies are ultimately need to pay for this production. And so with that, I thank you for your attention. And again, I'm glad to stay. I know folks have time constraints if you're at work or that sort of thing, but I'm a fanatic, so I'll stay. I'll stay for as long as anybody wants to ask a question. And certainly, if you send an email to this address here with any questions you think about later, or particularly if you would like a copy of the case study that documents what we did at Yew Creek, I'd be very glad to send that to you. And I'm very excited about having an opportunity to to see what's going on here at Martha's Vineyard and to see the incredible potential that you have here. You've got a major fire risk sitting in the middle of your island and little pockets all around, and you've got a great tool for mitigating that. So I hope we'll be able to do a demo project here on the island soon. So again, thank you for your attention, and I'm glad to answer any questions.
Thank you so much, Ken, for sharing your knowledge with the island. We do have a couple of questions about the methods of charging the biochar once it's made, particularly with the compost. One question was, does charging the biochar compromise the nutrition of the compost since it's leaching those nutrients?
Great question. And the answer is no. And the way I explain the analogy that I've used for my students in the past to explain how this works is that if you have a city with 100,000 parking places in it and 110,000 cars circling around looking for a parking place, right? When one car pulls out, another car pulls in, right? Well, that's the way ions work on an ion exchange surface, either humus or clay particles, or in this case, biochar. So when you charge that up and you put it in the soil, the ions that are already in the soil are going to be looking for parking spaces. The ions that are stuck to the char are going to be hopping off and hopping on. So you're not going to get a net loss. In fact, you'll get a net gain because there are, there's always going to be ions hopping on and off, and they're going to be in the soil solution available to be absorbed by plant roots. So that's a great question, but the answer is once it's charged, it's a cation exchange, or an ion exchange surface that are going to allow those nutrients to hop on, hop off, hop on, and not disappear when there's a rain and water leaches away into whatever waterways nearby. So, more water will stay in the soil with all the nutrients that are in that soil solution.
Great. And more on that, do you have an idea of an ideal ratio of biochar to compost material and how you would add that biochar to the compost?
Let me see if I can remember correctly. That slide that I showed with my friend Don Morrison standing there to his compost pile, it was one part biochar. And I can go back and look at that slide and give you the number, but my memory is that it was 1 part biochar, 6 parts compost, 16 parts grass hay. Okay, so not a lot, but with biochar, up to a point, more is better. But you want to make sure that there are enough nutrients in your compost in the first place to fully charge up that char. So it's not going to be, pulling nutrients out of your soil when you add it to your soil. And as I say, in a forest situation, when we're just using biochar as a service, we just pitch it as far as we can away from where we made it, and let the critters work it into the soil, and rain and material, ions dripping out of the trees and things like that will eventually charge it. So we don't worry about charging it when we're using it on the forest floor. But when you're using it for compost or in your garden, you absolutely have to charge it.
And do you have on hand a reference for a successful large scale operation that's incorporating biochar and compost?
Go to that slide with with that report that's gonna come out, and you can you can read the abstract, or the summary of it online right now at that website that I gave you. But in the chapter that the agronomists wrote, there will be a lot of that in there. But that difference in wheat growth that we saw, that slide from Spokane, that was 8 tons per hectare, 8 tons per hectare. So so it's not a trivial amount of biochar. I have seen there's another and I've been trying to, I saw it and I've been looking for it ever since, and I haven't been able to track it down again. But there's a Midwestern farmer that's been doing a really cool thing where he's been going along the sides of his rows with a fertilizer injector and injecting carbon in a slot right along the sides of the roots of his plants. And so he's putting the char right where it needs to be, right next to the roots of the plants. And as many of you folks who are agriculturists, agronomists know, more and more and more industry, large industrial agriculture is moving more and more toward no-till farming, because as soon as you open up the soil, you expose that soil carbon to oxygen, and microbial activity takes off, and you wind up getting a lot more carbon dioxide going into your atmosphere. So the less soil disturbance you can do getting that biochar into the ground, the better, the more of your soil organic carbon that's already there will stay there. So I really like that idea of cutting the slot in along the side of your rows of, I can't remember whether it was, I think he was a soybean farmer. Excuse me. And he just put a slot of char right next to the roots. And I thought that was brilliant.
I believe the name of that report you say that is coming out soon is called Biomass to Biochar. And
maximizing the value.
yeah.
And that's we're trying, we're really trying to, I mean, we live in a capitalist society. We have to monetize this stuff. If we can't, if we can't get paid for the services that we do, we can't make this work. And so that's kind of largely the aim of that report, is to, first of all, explain what it is we do at all the different levels. And here are the opportunities to scale up in terms of making bigger equipment, or scale out in terms of making lots of crews that can carry around kilns like we have and get out into the woods and capture some of this stranded carbon to capture it in long-term storage.
Great. Next question is about, does prescribed burning efficiently incorporate biochar into soil, or is burning in a kiln and then spreading the desired method?
Broadcast burning is a practice that that's been done for decades in the Northwest, ever since efficient tree harvest, ever since clear cutting evolved after World War II, when mechanization and chainsaws and the ability to whack a forest down from ridge to ridge. That's when broadcast burning and plantation forestry evolved in the 50s and 60s. And in that case, yes, you burn all that slash after you pull the logs out up to the landing and put them on trucks. They just they have drip torches and walk around the edge and light those. And boy, you see mushroom clouds popping off the mountains all over the place. And of course, that's incredibly inefficient, incredibly dangerous, because many of the fires all through the 50s, 60s, 70s, 80s were called slop over fires from these field burns. And so, as I say, we saw that those pictures that look of burnt little sticks that looked like the hair on the back of a dog or something, right? I mean, that's production forestry in Oregon right now. And I'm looking at a Douglas fir beam in this house right here that came from that kind of plantation. So as I say, there's a reckoning coming in the forest industry in the Pacific Northwest and in the North in general, where it's going to become riskier and riskier and riskier to do forestry like that when you can have a forest that can burn down from one side to the other. And so what people like me advocate is single tree selection and group selection harvest, and thinning from below, where you take the smallest trees and leave the bigger trees, because the bigger the tree, the clearer the grain and the more valuable the wood. So 4 small studwood trees would make up the volume of one of these larger trees, but the value of that larger tree would be 3 or 4 times the value of those same volume of smaller trees, because of grade. So right now, the southern slash pine growers are making 2x4s cheaper than we can make them in the Pacific Northwest. And so why don't we concentrate on grade? We're making lumber that nobody else in the world can make in terms of its beauty, its strength, and its consistency. And so getting away from broadcast burning and plantations would allow us to get in there and do the single tree selection and take the slash and burn it in kilns, so that we don't have to risk our forest by underburning those forests. We can do safe and site intensive production of that char, and you're going to get a lot more char per feedstock, because a broadcast burn, again, not too different than a pile burn, is going to give you maybe 5% of that material is going to turn into char, and the rest of it's going to turn into smoke and CO2.
Great. And there's a question about the ideal volume to surface area ratio for the most efficient biochar kiln and efficient burn and carbon conservation of a kiln.
Right. Again, we would love to do controlled experiments with kilns of, with different ratios and burn them 5 times with the same fuel and, send all those results to the lab and do all that good stuff. We haven't been able to get the grant money so far to do that. So as I say, this is based on expert opinion. Kelpie and me and a couple of other folks that do this have kicked this idea around, and it's our experience. And unfortunately, it's very qualitative and not quantitative. But we feel like, like a 3-to-1 ratio, 30% seems to be about the most efficient, because as I say, bigger surface area means more of that fuel is getting more oxygen. And so you're going to have more combustion and less char. You're going to get more ash. Too small, and you're going to have too much unburned stuff in the bottom of the kiln. So we know that our kilns that have those ratios produce the kind of char that, efficiently produce the char that gives us the greatest amount of production of char for the feedstock that we put in. And again, since we look at biochar as a service rather than a product, we're not so concerned with how perfect that char is. When we first started out, we were overburning our kilns because we got these unburned things in the bottom of them. And we felt like, well, so what? So, we're not putting it in a bag and selling it at the farmer's co-op. And so if we're a little inefficient, but we capture more carbon in the process, well, then we've met our goal. So, but anyway, getting back to that surface to volume ratio, it's just based on experience with the kilns that we build and our experience with what comes out of those kilns on the other side.
Great. There's interest in knowing about the potential for biochar to absorb excess nutrients from streams, ponds, and estuaries. If you could touch on that a bit.
Yeah, you've probably all seen those little tubes of chips in a mesh bag that people use in road construction and stuff to capture silt to keep silt out of the stream. A product that I think would be really awesome that could actually use the waste heat from biochar production. If you could, and there's something where there's really a major opportunity, engineering opportunity there, because, all that heat we produce is waste heat, right? It doesn't do anything but char the wood. So if we could capture some of that waste heat and char the outsides of these chips, put a little char coating on the outside, put those in bags and put them out, it would not only stop the silt from going into the stream, but it would adsorb the copper from brake linings and those sorts of things. Or in an agricultural system, if you have point source, well, let me back up a little bit. In an agricultural system, the runoff that you get into streams can be non-point source, which means it runs off the whole meadow and into a stream, all along the stream or all along a pond. That's a little more difficult. But if it's point source, where it's coming into swales or creeks and going into those ponds, you could absolutely, load up char in that and adsorb a lot of those nutrients. And then you could take those bags, you could literally pull those bags out like reverse tea bags and use that charge. That would be a great way to charge your char. Or these, the reason I suggested sort of a charred chip is because they'd last for a long time. Well, certainly biochar lasts for a long time too, but there's all different sizes. And so it would be hard to capture that in a bag and not lose all the small pieces out as it goes. But in terms of in terms of charging biochar, all those eutrophic ponds that are happening because of agricultural runoff, you could capture all that stuff in your char and take it out of there. The other thing you can do in a non-point source situation where you've got runoff coming down across meadows is if you can cut some slots in those meadows and fill them with biochar, or better yet, put a bunch of your feedstock in there and light long trenches of char. And the water ran through those trenches on its way out. You could pick up a lot of those nutrients there and then potentially plant those. That's what I'm suggesting to folks that I'm working with in Guam, where they've got progressive badlands forming, where once they lose one piece of ground, it erodes the next piece and the next piece and the next piece. And so what I'm suggesting there is that we make biochar in trenches perpendicular to the hill, because they're trying to protect a marine reserve down below. And a lot of the runoff that's coming off these badlands is just dumping silt and various, other materials onto these, very rare tropical reefs. So making swales perpendicular to the slope and making the biochar right in the swales, I think would be a great way to stop and then ultimately reverse that. Because then if you planted the rainforest trees that are no longer on that site into those areas, they could persist long enough to expand those little islands of diversity back out and reclaim those badlands into productive forests again.
Great. We have a question from Dan Doyle of the Martha's Vineyard Commission, who is thanking you, Ken, for customizing for Martha's Vineyard along the way. But do you know if there's a good regional resource with expertise in this area that us islanders should be aware of?
You have an NRCS and U.S. Fish and Wildlife. I think the closest one is based in Providence. So you do have, there certainly are resources available. And as I say, those couple of those government agencies have recognized the value of char and are interested in promoting its production. And so originally I was just going to come and talk about what we were doing in the West, but I became more and more fascinated by what's going on here at Martha's Vineyard. So I tried to find more and more out about it so I could connect the dots with Martha's Vineyard. So those are the two sources that I can tell you are, happening all over the country. As far as what might be regional, sources of support here, I unfortunately can't help you out there, but I'm anxious to do more research myself, because I really become quite hooked on this Martha's Vineyard problem here and potential solutions here. And I just see really amazing potential here for char. I mean, I know I sound like an evangelist, and I am, but I'm biased, but I'm really excited about the opportunity for biochar here. And so I'm guessing that you also have, that you have various land conservancies here that would, probably be interested